Okay, good afternoon. Welcome everyone to the 9th and final session of the autumn 2021 SunoikisisDC Digital Classics semester. This program has mostly been around digital philology and digital linguistics and digital editing and various issues around that. And this session will wrap up several of those themes and show us a glimpse, the beginning, if you like, of a world of slightly more advanced computational philology and linguistics. We're joined today by Alek Keersmaekers, who's going to give a general introduction and also one of the two case studies, and by Martina Astrid Rodda, who is going to give the other of the case studies. Both are early career scholars in classical studies and classics with a very computational linguistics focus. Before we start, I just want to give a very quick view of where this session fits into the rest of the semester, and also a reminder to the live audience, anyone who's watching us literally now at 4:15 GMT on December the 2nd, that you can join the conversation by leaving comments in the live chat feature. Please drop in a comment now to let us know you're watching. Tell us where in the world you are. Leave comments or questions at any time, and we'll try and come to them. And at the end, we will have a more general discussion, which we very, very much want you to take part in. So just to very quickly recap this semester, I'm looking at the program now that you've probably seen if you've been following. No, wait a minute, that's the wrong semester. Best laid plans and all that. Wouldn't believe I prepared this. Okay, this is the rest of the semester that you'll have seen if you've been following this this program. And so, as I said, this session on computational linguistics is sort of the last, and in some ways the most technically advanced of these sessions. And we had earlier sessions on philological search tools in week 1, text analysis in week 3, tree banks in week 5, translation and text alignment in week 7, and annotation in week 8, all of which had some linguistic and digital content that in most cases involved an existing tool or interface that enabled us to do a small subset of digital analysis on whatever texts were available to that tool. So the philological search tools, they were almost all tools that existed online, and whatever texts they have available to them, whether that be the corpus of papyri or Greek literature, Latin literature, or otherwise, the tools can act on those texts and give us, fairly advanced but constrained and finite set of results. The Voyant tools that we used as the text analysis example is slightly more flexible in that it has several tools inside it, a couple of dozen tools built in, and you can implement those tools on basically any text that you like. As long as you have a digital copy of it, you can upload it to the site or to your own version of the tool, and run these various different analyses on it, and you can see all different range of visualizations. There's still a limit to what you can do because they've only implemented a couple dozen of the most obvious text analysis and text visualization features in that tool. The tree banking and text alignment sessions were about very specific functions. Morphosyntactic annotation and the creation of alignment pairs manually or semi-automatically, respectively. And these were both really nice interfaces for us to use to annotate and create the data. But also there was some discussion in both sessions of what you can do with the data once you have created that data, what you can do with a large corpus of tree bank data, what you can do with a large corpus of aligned pairs across languages, and the sorts of linguistic and other research you can do with those data sets. In the text annotation session, we talked a little bit more about things like named entity recognition, and which is one example of natural language processing, which is starting to be the sort of thing that you can do more advanced work with once you get into computational linguistics proper. So not necessarily using these very easy to use interfaces, which essentially any classicist could probably use, but starting to get to where you have to look at a bit of code. A lot of this code has already been written. I think both Alek and Martina will show us code that, or will show us work that has been done with code that they have partly adapted, but they've also partly reused existing code and code bases and so forth. But it's really taking opening the vistas of the possibilities much wider. So having sort of put it in that context, I think we'll move straight on and invite Alek to get us started.
Thank you, Gabby. Let me go to my slides. Okay, so I will first give a very brief introduction about classical computational linguistics specifically. So first of all, what is computational linguistics? Well, we can simply look it up in a dictionary, and then we find that computational linguistics is basically any type of linguistics that uses computational methods, which of course is very obvious. But this definition reveals that there is a lot of linguistic work that is called or that is under the nomer of computational linguistics. So first of all, we have computational analysis of linguistic data, where we try to explain patterns in linguistic data with computational methods, so-called corpus linguistics. And then we have natural language processing, or computational linguistics proper, you could say, which is used to describe automated processing and or annotation of linguistic data. So what about classical computational linguistics? So most of a lot of work in classical computational linguistics has focused on the compilation of corpus resources. So right now we have a large amount of corpus tools for Greek and Latin. So for example, we have large full text databases such as the TLG, such as Perseus, such as some other sources for inscriptions and papyri. But then we also have texts that are annotated linguistically. So for things like lemmas, for things like morphology, syntax, semantics. So we have both automatically annotated text, large corpora for Greek and Latin, such as the diaeresis corpus or the Latin IC corpus, which has several millions of tokens of Greek, and then we have somewhat smaller, but still it's quite a large collection, as we will see in a moment, of manually annotated text. So these are called tree banks. There has already been a session about tree banks, so you know everything about them probably. So they have annotations like lemmas, morphology, syntax, sometimes even semantics. And so there is quite a bit of corpus-based work for Greek and Latin using these resources. So here is just an overview of these tree bank projects that we have for Greek and Latin. So as you can see, quite a lot of data, about 1.5 million tokens for Greek and about 1 million tokens for Latin as well. So there has been a lot of work on corpus compilation, but there has also been some work on natural language processing, so automated processing, although the field hasn't developed so much as for modern language. And one reason is that these methods usually require large amounts of data, and of course, as you all know, we're limited with the data that we have for Greek, that we have for Latin. So I've listed some examples of automated processing on the slide. So things like morphological processing, so things like named entity recognition, syntactic parsing are all parts of computational semantics, and we will see 2 more case studies later on. And important to mention that and it's important to mention that there's currently something called the Classical Language Toolkit, which is a Python library that enables people to use automated processing tools for classical languages in a user-friendly way. So if you're interested in that, you can also check out the earlier sessions that have been on this Classical Language Toolkit. What these methods usually have in common is that they make use of machine learning or artificial intelligence, you could say. Now, how does this work? So we have 2 types of machine learning. So first of all, we have so-called supervised machine learning, which refers to the computer learning information about something, about a certain class, for example, the syntax of a Greek or Latin word, and it learns this from a large corpus. So it looks at a lot of data. It looks at interesting information about this data, the so-called features. It learns patterns from this data and formalize them in a mathematical model, and then use this mathematical model to predict labels for new unseen data. So how does this work? For example, we have case information in a corpus, and from this case information, a computer can learn, well, if you have an accusative, for example, the word is very likely to be an object rather than a subject, for example. So that's supervised machine learning, but then we also have unsupervised methods, so-called clustering methods, where we don't annotate our data for class labels, but we simply let the computer look at our data set and divide it into several groups with similar members, so-called clustering techniques. To finish, what are the main challenges for classical computational linguistics? So there are certain typological characteristics of Greek and Latin that pose a challenge. So most NLP methods, natural language processing methods, have been tailored to English. And of course, there are some difficulties, well, some differences with English. So for example, Greek and Latin is highly inflectional, and they both have a rather free word order, large rates of ellipses, and so on and so on. And then we also have, of course, the enormous genre and diachronic variations. So many methods for modern language typically use things like newspaper data or Wikipedia data, so very homogeneous data. But of course, for Greek and Latin, our data is far more diverse, both genre-wise and diachronically, sometimes also dialectically, and so on. And then, I already mentioned this a couple of times, there is a problem of data sparseness. So we simply don't have as much data for Greek and Latin as for the modern language, which implies that we have to find methods that can learn useful things about language without as much data as we are used to for modern languages. Okay, so like I said, a very brief introduction. So now let's go to the first case study, which will be presented by Martina.
Well, thank you very much, Alek. That was all of the things that I would have said and more. So yeah, I'm just gonna say it's great to be on this seminar in particular, because I am very much the kind of classicist who has needed this seminar in the past, in fact. So it's very, very good to now be sharing my work. And the work that I will be sharing is part of my PhD thesis, which I have thankfully finished. And it's one application of those fancy computational linguistics methods. And we'll see what the problems are and what the actual sort of advantages of doing this kind of work are. I haven't done a remote seminar in a hot minute, which sounds unhinged at this point in the pandemic, but so I will only be able to see my slides, and if anything goes wrong, I will need one of you to yell at me, essentially, because I can't see the screen. But I think everything should be fine. So I will be talking about distributional semantics and Homeric formulae, and don't worry, we will define both what Homeric formulae are and what distributional semantics is. So I'm a Homerist. I work on archaic Greek epic poetry, and I will be shortening archaic Greek epic poetry to Homer a lot. It's not just Homer, there's another poet called Hesiod, there's a small corpus called the Homeric hymns. But the main thing is, archaic Greek epic is, we understand it to be the result of an oral tradition. So these poems were performed by professional bards, and this oral tradition led to a highly codified language, which is built around the repetition of phrases. And these phrases are called formulae. So formulae are repeated phrases that express a more or less reliably predictable meaning. And in classical studies and in Homeric studies, there tends to be this dichotomy between the oral traditional style of archaic epic poetry, which is based on repetition, and the creative style of written poetry, which relies on variation quite a lot. It relies a lot on unpredictable stuff and uses this as a vehicle for individual expression. And the central question behind my thesis work has been, is this actually really a thing on a linguistic level? And so in order to do so, I have looked at the ways in which these repeated structures, these Homeric formulae, can vary along two axes. One is the axis of what I call syntax, which we will not be talking about, but it has to do with the shape of these phrases. Are they always repeated in the same way? Are they flexible? We already knew they are flexible, but how far are they flexible, and does their behavior still somehow differ from what we would expect from a completely flexible, completely sort of standard kind of phrase that is not formulaic? And the other axis of variation is semantics, so meaning. And the central question on the meaning side will be, what holds a formula together in the performer's head and the audience's head? So how do we know that some specific things that appear together quite a lot are formulaic? Is there something more to the meaning of a formula than the fact that they appear a bunch of times in the same sort of shape? And I have approached both of these questions through a quantitative corpus-based approach, and I've given you a reference to Jensen and McGill Library 2017, which is very much like, it's a book that has as possibly its main goal to set out why a quantitative approach is desirable in ancient Greek linguistics. So, some thoughts on method before we actually go and look at some Greek. So if I'm trying to see why the behavior of formulaic expressions is unique, and in what ways it is unique, first of all, I need something to compare it to. I need a baseline of structures that will need to be as similar as possible to the formulaic structures that I'm looking at. But also, they will need to be non-formulaic, crucially. On the other side, I will need to be able to look at formulaic material only. So I want to have just formulae on one side, and I want to have something that is as close as possible to my formulae on the other side, but is crucially non-formulaic. So first of all, I just want to give you a very, very short account of what happens with syntactic variation. The syntactic variation, I have been comparing formulaic phrases that are made of an adjective and a noun to non-formulaic phrases that are made of an adjective and a noun. And they behave very differently. Formulae are used flexibly. They're not memorized by rote, but formulae can be changed, that can be adapted to the syntactic context in which they occur. In some specific ways, you are very free to add additional material to a formula. For instance, you are not very free to do things like change its case and number, or, since these are adjective-noun sequences, turn them into noun-adjective, or vice versa, so change the order, or split the noun and the adjective apart and add some stuff in there. So these sort of things, so changes in word order, separation, changes in case and number, are not very common in formulae, while they are very common in non-formulaic phrases. On the other hand, addition of extra stuff, for instance, of extra material, is totally common both in formulaic phrases and non-formulaic phrases. So there is something going on that is different between formulae and non-formulae. How do we explain it? Well, it's a lot easier in performance if the core shape of your formula stays the same and you just add things to it, as opposed to just like changing things around and moving things around. And we can see some patterns in formulaic flexibility that can be compared to patterns in the flexibility of idioms in English or other modern languages. So all cool on syntactic variation. What about semantic variation? What about meaning? So, well, I love that this slide still says insert citation. We're truly doing so well here. There was a citation here. Who knows what it was? Anyway, there is such a thing in the study of linguistic constructions and idioms as constructional preemption. Constructional preemption is the principle that says if you already have a really good phrase, a really good way to say a specific thing, if you already have an idiom that means a specific thing, you are less likely to create a new one because you already have one and you like it. This is not a law. This is a tendency. For instance, in order, like you can say, let the cat out of the bag for, spilling some information that you're not meant to spill. You can also say spill the beans. It's two idioms that express more or less the same thing. Maybe they have different connotations. Maybe they are used by different kinds of speakers. Maybe they have a different register sort of associated with them. But, so this is a tendency. It has counterexamples. But at the same time, a lot of the time we tend to find one set phrase for one thing and not, 3, 4, 5 of them. Formulae also kind of do this. So when the Homeric, sort of the archaic Greek epic poet, already has a formula that expresses something, they will tend not to create a new one that expresses the same thing and has more or less the same metrical shape. So what we would expect is that formulaic material will show more variety in meaning, by which I mean if we already have, like if one formula has one meaning, essentially, we will have lots of formulae, lots of meaning, as opposed to having more than one phrase that expresses a given meaning. I think I've said meaning a thousand times by now. So what I want to look at is whether formulae have more or less meaning variation than regular phrases. How do I do this? I need a way to quantify meaning. And this way is provided by computational linguistics, well, a linguistic approach called distributional semantics, which is widely applied in computational linguistics, not to ancient languages, but to sort of modern languages. And computational semantics, distributional semantics, is all about operationalizing meaning as a function of lexical context. Words are more similar to one another, the more often they occur in similar contexts or in the same context even. How do we do this? So I've given you some examples here on slide 9. We have two words, wreath and bow. Sorry, bow, not bow, bow. I love how I chose two words that I cannot pronounce. This is truly the English learner experience. Anyway, we have wreath and we have bow. All of these occur with a bunch of other words in these made-up examples that I have created. And we also had philosophy in a different example, and I forgot to take it out. So we tabulate these co-occurrences. We look at, bow co-occurs with the adverb safely once, it co-occurs with curved, the adjective, a couple of times. Wreath does not co-occur with curved ever, but on the other hand, it co-occurs with beautiful a bunch of times. And philosophy also has its own patterns of co-occurrences. We can take the most significant of these concurrences, and we can turn them into the coordinates of what we call a vector space model. So we will place every single one of these words in this space, depending on how often they concur with our context words. So in this case, we have we've picked two context words, beautiful and safely, and we can place our three target words, breathe, bow, and philosophy, in this space, depending on how often they concur with these context words. And if we scale this up to the entirety of the lexicon of a language, we end up with a massive vector space model in which every word has a position, and words that are closer in meaning will also be closer in the vector space model. So then we can use relations of space to express relations in meaning. Cool. So I've applied all of this on Homer. I've built a vector space model. Well, in fact, we have, me, Baba McGillivray, and Philemon Probert, my PhD supervisor, built a vector space model from the diaresis corpus that has been already mentioned, I think, a couple of times in this series of seminars. We evaluated it for accuracy against a bunch of ancient sources and modern sources. We figured out that it's the best vector space model for the kind of thing that we wanted to do. And we immediately run into a problem. Distributional semantics is an approach that is normally applied to huge corpora, English language corpora of the size of, the entirety of the internet, basically. Is our corpus too small for distributional semantics? Turns out it's not. We had a look at a small set of transitive verb formulae, and I'm not going to go through this whole slide because I'm running short on time, but we found out that there is a way to measure the distribution of the objects of these transitive verbs that actually gives us some interesting results in terms of the formula type tends to shape the meaning of the objects of this formula. So our corpus is not too small. What happens if we look at all of the formulae that contain a transitive verb plus an object? So I've looked at a bunch of them. How do you extract a transitive verb plus object phrases? Well, you use a tree-banked corpus, about which you should know pretty much everything by now. We use the ancient Greek and Latin dependency tree bank, and this being a tree bank corpus, it contains information such as which accusative nouns are the object of which verbs. So if I find many naide, the relationship between these two words is codified in the corpus. So I've extracted this information, and I have isolated 15 formulaic verbs. Each of these has at least 10 objects in the accusative. And these are all formulaic. How do I determine whether they're formulaic or not? Well, I look at the work that someone else has done before me. And there are two complete editions of Homer and Hesiod with the formulae sort of identified as such. So I've relied on an independent sort of definition of what a formula is. So that is our target corpus. That's our formulae. I need, as we were saying at the beginning, I need a baseline to which to compare it. And for the baseline, I've looked at a verb valency database that Baba McGillivray put together and that we're planning to release very soon. There's an article in the works on all of these results, and it's already been used in the other paper that I put in the bibliography here. So it's a bunch of authors, Aeschylus, Aesop, and so on. None of these are Homer or Hesiod, as you can see. So these are non-formulaic. I am comparing them to formulaic material. What am I looking at? So I have my list of verbs. Each of them has a bunch of objects. I am measuring how closely together these objects fall in the semantic space. To use this, I can use a measure of similarity that is called cosine similarity or cosine distance, which measures the angle between the vectors representing each of the objects. And I've given you a visual representation. It's actually really, really clear. So the cosine distance is the cosine of the angle theta between two words. In this case, we've called them item 1 and item 2. So I have the distances between all of these words, and specifically what I want to figure out is the centroid, the center of this cluster of objects in the semantic space. And I will look at the median similarity and the variance of the sort of various distributions of objects for all of these verbs that I've listed here. Oh, and you can find my code here in my DPhil thesis repository on GitHub in case you want to play with it. Have a look. It's all in Python. It should all be relatively accessible, not least because if it's accessible to me, it's probably accessible to the average classicist, not a very competent coder. It all works. Gabby has, looked at it, but, Baba McGillivray has also looked at it, but don't expect elegant code. And I think this should be encouraging in terms of you can do this kind of work even if you can't write elegant code, as long as it's functional. So what did I find in all of this comparison of formulaic and non-formulaic material? On the one hand, I want to say nothing, but that's not true. I have found a negative result. So I find that there is actually no difference between formulaic and non-formulaic pairs of verb plus object. So the range of the objects that a verb can take in a Homeric formula appears to be more or less the same as the range that the same verb can take in a non-formulaic construction. There are also no significant effects of frequency or productivity. So what the hell happened to our initial prediction of formulary economy? If formulary economy were a thing that we can measure in this way, we would expect the objects of formulaic verbs to be very, very varied in terms of meaning, because we don't want more than one object that expresses sort of a related meaning to some other object. But we don't find this. We just find nothing. Like, we find no significant differences. So what do I do now from this negative result? I want to look at my data again. I want to see if the similarity measure that I have used is the best one. I don't think it necessarily is. Maybe I want to look at whether there are clusters of related words in my data, as opposed to just like where the center of a group of words is. I want to control for confounding effects. I've been comparing stuff that is written in hexameters and in a poetic dialect of ancient Greek to stuff that is written in prose, in a bunch of other meters, in a bunch of other dialects. So let's maybe take something else that is in hexameters and in the epic dialect, but it's not formulaic. And I can look at later hexameter poetry for the sort of Greek scholars here, Apollonius, Quintus of Smyrna, Anonymous of Panopolis, to see what their verb-object phrases do. And maybe in the end, I will figure out that there is actually no difference. And then we will need to rethink how the concept of formulary economy compares to a bunch of other things that we would have expected it to compare to, like constructional preemption, but it turns out maybe it doesn't. So, final question, can we use distributional semantics to learn about formulae? Maybe we can. More work needs to be done. But generally speaking, I think this is a really encouraging start in in showing how we can apply these sort of methods to ancient languages, even without having huge corpora. The results are still there, and they can sort of give us a new perspective on stuff that people have been discussing for the last 100 years. Thank you. That's me, and I'm quite happy to sort of yeet the ball back to Alek for his presentation. Thank you very much.
Thank you. Back to you, Alek.
Okay. Thank you, Martina. So now I will talk about something which might seem completely unrelated to what Martina just said, and it is quite unrelated, but as we will see later on, there are some similarities. So I will talk about automatic morphological analysis of Greek. I have something else to point out. There is another name on this PowerPoint, so Wouter is a PhD student who shared part of the work that I will present now, and we also presented a version of this work in the past.
Your screen's not currently shared, Alek.
My screen is not shared. Oh. Okay, now it should be shared. Okay. Okay.
Yes, there we go.
Yeah, so now you can see, yes. Okay. So I will talk about morphological analysis. So first of all, part of speech tagging is probably one of the, or part of speech tagging or morphological tagging, part of speech, because it was originally developed for English, and as you know, English doesn't have a lot of morphology. But so part of speech tagging or morphological tagging is probably one of the oldest tasks in natural language processing. And how is part of speech or morphology predicted? Most approaches use the context of a word to decide on the correct morphological analysis. So, for example, we have a Greek sentence like "al agatai tuchei." Tuchei can, of course, be noun or verb, but we are pretty sure it's a noun because it's a dative feminine noun because it's preceded by a dative feminine adjective, for example. So this is the kind of information that such older methods use for part of speech tagging. And these patterns are automatically learned from large corpora using supervised machine learning techniques. So we have a large corpora where we have all kinds of patterns like dative feminine nouns are likely to be preceded by dative feminine adjectives. As for the context is of course a very vague term, but it's typically defined as a fixed number of preceding words. So like the four preceding words, for example. And there are some techniques that have been developed so that these part of speech taggers know which parts of the context are useful to look at. So, for example, here in the example on the slide, it's very clear that agatai is much more useful to define the part of speech of tuchei than al, for example. So this is the general overview about how all the part of speech tagging systems usually work. But of course, there are some problems with ancient Greek. So, for example, ancient Greek morphological texts are very complex. So we don't have noun or verb or singular noun, maybe a plural noun, and singular verb and plural verb, maybe. As in English, but we have very complex part of speech text, like, for example, it's like participle, singular, aorist, active, masculine, dative, which of course increases the number of possibilities that the part of speech can take into account. So what is usually done then is to split this complex part of speech tag into individual attributes, which are also predicted individually. So we predict whether, for example, we predict whether the word is singular or plural, whether it is active, middle, or passive, and so on and so on. The same is true for the context. So, for example, if we have a sentence like parusei tuchei, then of course we know that tuchei is a dative noun because parusei is dative, is also dative, and not because it's also present. Well, not because it's present, for example. Then there are some other problems. So, for example, because Greek is so morphologically complex, corpora typically do not contain all given forms of each word. So, for example, if you look at Greek treebanks, which is 1.5 million tokens, which is quite a lot, but they do not contain a single attestation of the perfect participle. Masculine nominative lelukos, for example, and luo is of course not a very infrequent word. So I think you can see the problem. So if we confront the tagger with a new word, lelukos, that it hasn't seen a corpora, it doesn't really know what to do with it. So the usual solution is to give that tagger a morphological dictionary. So, for example, you have like the morphuse morphological analyzer, which is implemented in Perseus, and then we can say to the tagger, just consider the morphological tags that are present in this dictionary. So for example, for Tuchei, we know from its form that it can really only be 3 things. So there are some tagging tools that implement these optimizations that I just talked about for ancient Greek or for inflectional languages in general, and they are able to reach a relatively respectable tagging accuracy. However, they certainly cannot they certainly cannot predict everything correctly. So one problem is that these tagging tools typically use a limited syntactic context. So for example, 4 preceding words, and then if you have, for example, here oligon, which is normative because the main verb is st, but the tagger doesn't really know that the main verb is st because it only looks at the 4 preceding words. We can use a larger context, but then it doesn't become obvious that, for example, the word that's preceding the preceding word, for example, that the 7th preceding word is st is relevant for the automatic analysis of oligon. So in general, of course, the syntactic context is often highly important for Greek morphological prediction. So things like case, things like agreement are typically morphosyntactically phenomena. And then another problem is that the semantic context of a word is not used just just the part of speech text of preceding words are used. So even if we include st in the context, it's the tagger would only know that it's a verb and not a special kind of verb that typically requires a nominative rather than an accusative. So how can these problems be resolved? There are some models that are currently becoming quite popular, so-called neural language models. And these neural language models are actually kind of related to the distributional language models that Martina just talked about, but more about that in a moment. So what do these neural language models do? They learn information about the usage of a word, and usage is very broad. So this can be the syntax of a word. This can be this includes the syntax of a word. It includes the semantics of a word, and it learns this information automatically from a large unannotated corpus, so just raw running text. And the advantage of these models is that no handcrafted features such as what is the part of speech, so for example, what is the part of speech of the 4th preceding word is necessary. And then specifically some kind of there is a type of neural language models, so-called transformer models, which are becoming very popular nowadays. And this is because they're very good at automated processing of natural language sentences and learning this information about the usage of specific words. So these are models called BERT. Is a very popular one, for example. So what do these models use? They use a principle called transfer learning, and maybe the image here on the slide is a little strange, but I will explain this with a metaphor. So what these models do is they first learn general information, like I said, about the usage of Greek words from a large corpus. This step is called pre-training, and then extra information from an annotated corpus information about morphology, for example, if you want to predict morphology, information about syntax, if you want to predict syntax, is added to this network, which is called fine-tuning. So we can visualize this, for example, with a metaphor of making dough, for example. That can be so we first make dough, for example, and then we can use this dough to create a lot of different recipes. So we add things to this dough. So dough in this metaphor is like the pre-training of learning general information, and the types of cookies, for example, is like the fine-tuning step where the dough is molded into specific things. And the advantage of these kinds of approaches is that morphological and syntactic analysis don't become dependent on each other anymore, which avoids error propagation, for example. So if we first predict that something is a nominative while it should be an accusative, and then use this case information for syntactic prediction, of course the syntactic role will be incorrect, while with those transfer learning approaches we just learn general information and then we use this to predict morphology and syntax independently. So of course, I've been quite fake for now. So these models learn a lot of information about the usage of a word, but how do they do so? So what they do, and there we can see that's quite familiar to the methods that Martina just discussed. They use information about the context of a word. More specifically, they predict. These methods try to predict words on the basis of their context. So this can be done in several ways. So one method which we used, which is implemented in one of the tools we used, randomly replaces words by a plausible alternative. So for example, we have a sentence, the chef cooked a meal, and then it's replaced cooked by ate. And then the model has to decide which words are replaced and which words are original. So if, for example, it has to decide that ate is a replaced word and not an original word. And if the model succeeds for this task, this means that it has learned a lot of information about the usage of words. So, for example, if it can correctly predict that ate is a replacement, it knows that chefs are people that do cooking, for example. So in this way, the model learns a lot of information about the usage of specific words. But then we used such an Electra model for morphological tagging. So what we did is we fine-tuned the model for each morphological attribute. So all of them are listed on the slide, of course, you know. And so for example, we have a label such as person, and then we have 4 possible labels, 1, 2, 3, and then also another label for all words that do not have a person. So things like prepositions, things like nouns, and so on and so on. So we trained this model on a large corpus, well, a relatively large corpus, 29 million tokens, which is actually quite small for this transformer model. So they usually use billions of words for modern languages. And then we enrich this model with information about morphology from treebank data. So first we used an older tagger, which doesn't use this neural approach, but simply uses the context of a word. And then we compared our model to this tagger. I think I can skip most of what is on this slide, but so we So what we did is we added some constraints to the text so that we do not have strange predictions, like, for example, this word is an adjective but it is a first person, and then we also constrain the output with further constrain the output with the analysis of morphs, so with such morphological lexicon, and then we see that we gain quite a big improvement. So in our final step at the bottom of the table with our original tagger, so the error rate is almost cut into half. So what kinds of text are easy to predict and what kinds of text are difficult to predict? In general, religious texts, for example, are very easy to predict. I don't think this is surprising. They use quite a simple language, not a complex morphology, and things like lyric poems are very difficult to predict, probably because they have a large amount of dialectical forms which weren't present in our dictionaries. And then if you look at the prediction for each morphological attribute, we see that attributes like mood, like case, like gender gain quite big improvements with previous approaches. Why is this the case? These are categories that are typically morphosyntactically often, like, for example, case, nominative, and accusative. This is, of course, a very morphosyntactic problem. And then we see that these models, which know a lot of information about the usage of words, typically have very good results. Yes, I can also say a little more about this. So one example is, for example, case. Like I said, there are big improvements with the classification of the nominative and accusative case, for example. I will just skip this slide. So this is just an overview of the categories that are still problematic. And then we took a closer look into the kind of errors that the tagger still makes. So of course, if we go back, 97% is of course quite good, but this means that there are still 3% of words that are incorrectly predicted. So what kinds of words are they? So one thing that's very striking is that actually in a very large amount of cases, or very large number of cases, our model actually made the right prediction, and our data our data or manually annotated data was simply wrong. So of course these treebanks are manually annotated, but they're not always annotated perfectly. Oops. And then there are also some things that are not really wrong, you could say, but simply inconsistently annotated in the data. So for example, we have a word like Armeniois, the Armenians. So is Armenian, is this a noun or an adjective? Of course, this is something you can discuss about. But what we see in our data is that these words are sometimes actually annotated as nouns and sometimes annotated as adjective, and there's not really any logic between the choice. It's simply a manner of annotator preference, for example. Then there are some cases where our model simply, so our models are quite good at understanding the meaning of Greek words, but they're not perfect. So for example, we have a sentence like from Homer, I guess this is tais mainonta leon edamas biefin. The lion overwhelmed him with his strength while he was still breathing or something, as mainonta polai several times. And in this case, for example, as mainonta was analyzed as a neuter plural instead of a masculine singular, because the model thinks it should agree with Pola. But of course, we know that things can't really breathe. So this is things that could theoretically be resolved with more data, so that we have a lot of data about the word asmainata, so that the model can learn asmainata is really something that a living object does and not an inanimate object, for example. Then these models are quite good at understanding the syntax of Greek sentences, but there are some problems, specifically also with elliptic context. So there it often makes a lot of mistakes. Then, as I said, we use the lexicon of Morpheus, but then not all Greek forms are in this morphological lexicon, especially dialectical forms. Especially dialectical forms, and the Tega often struggled with those forms. Then something interesting is that something that's very difficult to resolve are things like deictic expressions, so pronouns that refer to words in other sentences, for example. So, for example, we have a word like autos, which refers to a word in a previous sentence, and we only know the gender of this word because of if we know which words it refers to. But these models work on single sentences, so these problems are actually impossible to resolve. Then there are some more problems related to genre, dialect, diachrony, and then there are also some problems that are actually very difficult to explain. So these models use neural networks, which is a kind of machine learning model, which is often called a black box. So it predicts a certain output, but we don't really know why it made this prediction. So, for example, it usually does. Models do the mood of like Hina clauses. Usually they don't make a lot of mistakes with that, so they know that Hina clauses, Hina purpose clauses typically use a subjunctive, but then sometimes it makes the wrong prediction even in very simple sentences. So yeah, it's very difficult to explain why it does so. So to conclude, as we have shown, as I have shown, but of course this is shared work, these transformer models are actually able to make significant improvements, especially for difficult morphosyntactic categories, which is not surprising. These models are very strong at understanding the syntax, understanding the semantics of Greek words. And then there are some problems that are definitely resolvable. So, for example, by expanding our lexicon, but then there are several problems that are very difficult to resolve, even for human things like those complex, these complex deictic pronouns like autos, for example. Okay, this brings me to the end. And I'll give the floor back to Gabby, I think.
Well, to all of us, thank you very much, Alek, and both of you. The discussion in live chat so far is strongly suggesting that we hope you're going to use your expertise to bake us some cookies at some point, as that well-chosen metaphor has clearly kicked off mid-afternoon munchies. But no, thank you both very much. A reminder to people watching live, please do make any comments or ask any questions in the live chat there. It is for serious conversation as well as as well as banter. I might start with just a quick question that came out of one of your slides, Alek, but that both of you might have something to comment on. Was just that I noticed in your slide, I think it was the 12th slide in your last slideshow, results by genre, that certain types of text were much more easy to predict for your tool than others, and epic poetry, for example, only had half the error rate of drama or lyric poetry, for example. And I wonder if either of you would like to comment on and account for the differences between those, since it seems to be relevant to both presentations.
Yes, I guess I can start. So yes, like I said in the introduction, the genre problem is really a big problem for classical computational linguistics in general. So the genres are very diverse. It also is a big problem for semantics. I know there is also some work. I think Martina as well did something on this topic. So in general, it's of course a big problem, and there can be some ways to resolve these problems. Usually for modern languages, several models are trained on different kinds of genres, which is not really a big option for Greek. Which is not really a big option for Greek because we don't have too much data, and then we would just limit the data for it. But there are some other methods, so-called domain adaptation methods. But in the example, in my example specifically, yes. So at first I was also a little surprised, but I think what it shows is not that, for example, so that's something you might think at first sight. Well, these poetic texts are simply very difficult, which is partly true, of course. They use a very flexible word order and some other things. But they also have some easy things, like they usually have quite short sentences if we compare them to, for example, philosophical texts. They have more concrete word usages. So, for example, in philosophical texts, you have a lot of strange constructions. Well, strange constructions like those abstract terms, for example. So they also have some things that make them easy. I think for my case study specifically, but maybe Martina will add something about her experience. For my case study specifically, there is simply a lot of data from epic poems in the treebank material that we have, and not a lot of data from, for example, lyric poems. Quite a bit from drama. So I don't really know why drama is so problematic, but there is simply more data for epic poems. Also, the Morpheus tool typically recognizes all epic forms, while it might not recognize all dialectical forms in lyric poems, for example. So I think that's the big thing in my example.
Yes, so sorry, I have been fighting the YouTube chat to post the reference, and I think I have just been censored because the reference contains a link. Can you all see it or not? No.
No, but if you put it in private chat, I can post it.
No, I can also just like now
we're not,
here's, yeah.
We're not censored if we do it as.
Yeah, but also just like I've just put the actual reference and
Great,
the
great.
URI link you will just need to find on your own. But this is open access. Yes, I think this should have worked. Yeah. So this, if I recall correctly, this has a bunch of stuff about genre in sort of semantics, disambiguation, and that sort of thing. Yeah, as Alek was saying, the corpora are really, really unbalanced, which is part of the problem, and it's actually why I ended up going for the verb valency database. I mean, it also saved me a ton of work, but it's the sort of thing, yeah, like the having a balanced database as opposed to just going for a corpus of everything that is not Homer helps you a lot, because if you look for something that is like, you know, everything that is not Homer, half of it is going to be Galen, the sort of Roman era sort of scientific and medical writer, because he just wrote so much, and all of it is sort of well digitized, which is absolutely great. But it also means that, you know, a lot of what you're looking at is the same thing. I had similar problems with Herodotus in my other corpus for the syntactic study, because there is a lot of Herodotus, and Herodotus tends to use very Homeric language, so that's a pain. And I think we have a question. Is the link visualization on Voyant tools based on semantic distribution explained by Martina? Yes, exactly. Yeah. So Voyant tools has, I played a little bit with it as I was preparing this session. And it has a bunch of things that are actually really like based on distributional semantics and sort of, yeah, what words associate with other words, where, like, how can we say that words are more similar to one another just based on textual data? So 100%. And one of the exercises that I've sort of suggested you could do after this session is very much about try and play with the sort of things that you've done after the Voyant tools session, and how would you do them if you could code your own analysis, essentially.
Cool, thank you. Any other questions? Or Monica, go ahead.
Yes, I have a question about Homeric formula. So you presented, and I would like just to ask a question also for our students, because Homeric formulae are, well, a very important and specific problem. And basically, they ask us to move from textuality to orality and back from orality to textuality, because we know that they were a device for oral performances. But now we have what we still have of Homeric poems. They are in a fixed form. We know that in a certain period of time they were fixed. But in your work, and you showed us specific problems about the use of verbs and objects, etc. But how much can we get using these methods for studying these how Homeric formulae were so flexible? So of course there is a problem about the data we have, because we have we have a version, of course, of the Homeric poems, just one of the many possible versions we could have. So how much can we understand about the use of Homeric formula in an oral context? What can you say about that?
Yeah, absolutely, sort of central question to everything I've been doing, honestly, on Homer. So one of the things that I tried to do for my PhD was, let's step away from this sort of reified, solidified orality versus literacy dichotomy, and see what this language actually does when it is used. And, you know, to look at how it's used, we have to look at the texts we have, and we have them as texts. And on the one hand, the really, really encouraging thing is that if you look at the way flexible formulae are used in poets that we know are operating with writing and not with orality, and I've looked at Apollonius of Rhodes, there are very clear differences in the sense that Apollonius seems to be deliberately manipulating and doing some things that Homeric formulae cannot do. And of course, since we know that Apollonius was a poet who worked with writing and was very interested in the possibilities of writing, then we can say, well, this is because he's trying to do something new compared to Homer, who was oral. But the Homer who was oral bit is, of course, our own pre-existing assumption. So this is something that I've kind of been sort of butting heads with a little bit in all of my work. And one thing that I'm really, really interested in is how much we've made the assumption that formularity is a thing that only happens in oral traditions, when we have an entire sort of living tradition of formulaic expressions, and that's the internet. Internet memes are an absolutely archetypal example of formulaic expression, especially memes in the sense of like linguistic turns of phrases, not, you know, the little cat pictures, as much as I love the cat pictures. And it's really, really interesting because internet linguistics also has this problem of, is this written or oral? Because the medium is clearly writing, and it has to be writing. And a lot of the things you can do, you can only do with the medium of writing, but the register is not. Like the way, like the things that we do are things that we do in speaking. So that's fascinating. Do I have any actual answers? No. Do I think this is interesting? Yes.
Well, yes, of course. Yes, we don't have an answer, and this is well, is not discouraging, and we don't have to be frustrated about that because we need answers. But anyway, yes, thank you, and I totally agree on that. And Homeric formula, or in general formula, are interesting because they are also about reuse. So this is something that we know in general for ancient literature. So the use of poetry. So also prose was versified for memorized text. So this is important in general for understanding those texts. So anyway, thank you for your answer. And this was also for, this is a very complex problem, of course, a very complex philological problem, but also for our students to get a sense. So today we have data, we have text, but of course there is a huge amount of stratification going back to orality and to a distant past. So this is multi-textuality. Anyway, so thank you.
Maybe just briefly, while we're waiting for people to think of more questions on YouTube, we could very briefly look at the exercise that you've proposed, and we could discuss that a little bit more. Does someone want to share it so we can just look at it quickly, or?
Yes, sorry, 1 second. I am also getting a link to something that people are doing in Oxford.
See if I can find.
Do you want me to share the page in?
I can do. I just needed to change which page I was sharing, which I think I've just done.
Okay. So, sorry. Yeah, yes, it is.
Right. So does someone want to talk through that just quickly?
Yes, I can talk through that, I think, because I am the one who kind of started throwing some things together. So yeah, so basically what we would like you to do in the exercise is to kind of have a reflective opportunity in a way on all of the various sessions that you have done in computational linguistics, and specifically the 2 sessions that required you to use environments that were already built for a purpose, and that since they were built for a purpose, they enable you to do a bunch of things, but they also constrain the sort of things that you can do. And one of you in the comments has already pointed out that stuff in Voyant tools is built on the same kind of approaches that I have talked about, and a bunch of other stuff in the search tools and in Voyant as well relies on the sort of stuff that Alek has talked about in his presentation. And ultimately, we would like you to think about, how would you play in the same sort of sandbox sandboxes that we've been playing at today, and the kind of sandboxes that you can find in the bibliography that we've added for the session. And, maybe, so you had some research questions from the previous sessions. Can we apply some of these methods to these research questions? And if you wanted to do that, what resources would you need? So in the same way as I rely on tree-banked corpora, I rely on this verb valency database. All of these are the resources that I need because they contain the information that is necessary to my work. And then you can look at whether these resources actually exist and where you would find them.
Yeah, and I think some of the questions that came out of the tree banking session, the text alignment session, might also be things you might think about in this context. And although people who are new to this won't necessarily know what all the possibilities are, I mean, we've had a couple of nice case studies today. The readings in the session will give us a couple more, so you can get a sense of the scope of the field. But also, feel free to be sort of think blue sky. If we had an aligned corpus of X, we could then do the following things and ask the following questions with it. The fact that that corpus doesn't exist, or we don't know whether or not it exists, doesn't need to be a barrier to us speculating like this. Although finding out whether or not they exist is, as Martina says, would be a very nice part of this exercise and this conversation. Yeah.
Yeah, I have slightly thought about what I was doing for the first month or so of my PhD on a very, of course, this is not going to be, don't design an entire PhD. I would recommend you don't do this. But the sort of work, it was like, oh, I would really like to think about this, but do the resources actually exist? Can I feasibly think of creating them? Yeah. Mm-hmm.
Yeah, I think this will lead to some very interesting discussions. I think more than anything else. I think that's what I hope will come out of this. Yeah. So I hope people appreciate that in what could have been the most technical of the seminars for this semester, we've given you the least technical and most talky exercise.
There are other comments in the chat. So
yeah, the one that I see that is a question is again from Anita.
Yeah, and I was just replying to this in the chat actually by saying that Dissect is the tool that I have used to build the various semantic spaces that sort of are used in both the couple of articles that I've linked and the work that I have described today. So yeah, absolutely. Relatively user-friendly, as in, again, if I can run it without crying blood, it's user-friendly.
And what is Dissect? Briefly.
Sorry. Yes. So Dissect is a tool to build semantic spaces. So you have to do a little bit of corpus pre-processing in order to feed into Dissect. You basically have, it takes concurrence tables for all of your target words and all of your context words in a corpus and turns them into semantic spaces, and you can manipulate these spaces in different ways. You cannot filter for stop words. You have to do it before that, but you can manipulate the number of dimensions and you can query these spaces afterwards. You can either write your own scripts to query the semantic spaces, which is what I did, or you can sort of query them on basic ways in terms of, how close are these two words, that sort of thing. That was a terrible explanation, but I think it gave more or less an idea of what we're talking about.
Yeah, certainly enough for someone who may not actually be going to use it this evening to get a sense of what it might be useful for. Yeah. Yeah. Thank you. Any other? Yes.
Alek, do you have something to say on the baby oil versus olive oil thing? Because that is exactly your thing, isn't it? How do we distinguish between these two?
I don't know in which. I think this thing was already quite a bit earlier in the chat. I don't know what's meant here.
I think the idea here is that, you know, on a surface level, baby oil and olive oil, you know, it's still, you know, modifier plus noun, but baby oil is all you put on babies, and olive oil is all oil made of olives, and it's kind of crucial that you don't mix the two up. You don't want to make oil out of babies. And, you know, that's the sort of thing that your models have to deal with, isn't it? Like this kind of ambiguity.
Yes, yes.
Yeah, they're not replaceable terms in the way that, you know, coconut oil and flaxseed oil might be replaceable with olive oil. Yeah. And I guess it's only seeing the uses to which they're, the context in which they're used, that helps you to break them up into different
Yes, exactly.
groups. Good. Any other questions or observations for the to finish us off? We have a few minutes left. I have one thing I want to say just before we finish, but not related to computational linguistics at all. So I'll save it until I'm sure we've run out of other things to say. I guess again, thinking of the question from the students, if a student watching this wanted to go a little bit further than thinking about these resources and to actually look at some resources, and this student didn't have any Python yet, but was bold enough to say, okay, give me some Python scripts and I'll try and run them and tweak them if there are instructions for how to do so, you know, that sort of level of things. Where would you suggest they start? CLTK, some of the scripts you've linked, Dissect, your own repository? What might be a relatively painless place for someone to start if they really just wanted to experiment with this?
I think the CLTK is a good option. So what they do is so you give them a text, and then they give quite a bit of analysis layers for its text. So it makes automatic morphological prediction, automatic syntactic prediction. I think there is also like a named entity recognition implemented in it, and so on. I'm not extremely familiar with it, but I think it's also not that difficult to use. Yeah, and the difficult part with most of these tools is that they typically are quite, how do you say, are quite finicky. Is that is that the right word about their input and their parameters? So if you don't really know what you're doing, and you just take some like for example morphological tagger from somewhere on the internet, and then try to train something or label your data, you might get a very strange output for some very stupid reasons, like I don't know. For example, it's expected decomposed accents in Greek, and the accents were composed like very reasons like that. So.
Yeah, and another thing I've sort of put in the chat, and I think has now ended up somewhere in the chat or not, is the Patrick Burns repository, DIY Classics, with a bunch of Python notebooks with various sort of small exercises that you can try to do on ancient Greek materials with sort of already written Python code, which is, relatively editable, or, actually quite editable. So that is also a place to look at. And also oh, sorry. No, I also just recommend having a look at the Jenset and McGillivray book, if you're more of a book person the way I am, because it does describe a lot of things that have been done and a lot of things that could be done.
And we've also got there in the chat a link to one of the links that that Alek had on his slides earlier to a Sunoikissis session from 2 years ago, which was introducing CLTK, which would also be a good place to start. That would have, some more basic exercises built in and some data that you can start with and so forth. Yeah.
And in the chat, there is also a link to a paper by Patrick Burns, and the paper is open access, so you can download it, and is a description of the CLTK. And is interesting because you also have a table with a list of the languages that are currently covered in the CLTK, not only Greek and Latin, but other historical languages. So also for those students who are following us and who are not studying Greek and Latin, there are other historical languages, of course, where you can use these methods. So just to have a sense, okay? So to contextualize Greek and Latin in the big frame of historical languages and the use of specific Python libraries for dealing with historical languages and also with Greek and Latin if we have a specific interest in those languages.
There is one more question. I don't know what this question means. I hope somebody else does.
Nope. Sorry.
I don't either. Orange.
Okay, sorry, we don't know what orange is. Apologies.
Which I think is also very much like the general vibe in computational linguistics applied to classics is always very much like there's so much going on in computational linguistics. There's so much going on in sort of digital approaches to languages that there's always someone who will ask, have you tried this thing? I'm like, no, I've never heard of it. Tell me more. Or, try it out and design your own case study.
Cool. Yep. So maybe someone will have figured out something about Orange in the next few months, and we can have a future session discussing that, if it works or not, if it doesn't. Great. Okay, so we are more or less at the end of the time. I do want to just briefly take advantage of the fact that I accidentally shared the wrong program at the beginning of the session to go back to that and sneak preview next semester's program, which is here. Am I sharing that? Yes.
Yes, this is the spring semester. Yeah,
thank you. Yeah. So the spring semester, just to say that yes, the autumn semester is usually the very philology and linguistics focused one, and the spring semester is usually much more. Well, it's very cultural heritage focused, so it includes several sessions on things relating to archaeological data and especially museum and other heritage institution data, a few sessions related to 3D imaging and modeling and virtual reality, and a few sessions related to geographical data in one way or another. So there's a very, very rich semester worth of materials there, starting in about 5 or 6 weeks' time on January 13th. So I hope you'll join us for some of that. And I'll stop sharing. Great. So thank you all very much again, both to all the people watching and discussing this with us live, and to Alek and Martina, and from Monica and myself, we'll be back next semester. See you all soon. Thanks a lot.